Welcome to Module 5, Unit 1. In this unit, we will learn how to build image histograms in MATLAB. A histogram provides a graphical representation of the distribution of pixel intensities in an image. By examining a histogram, we can better understand image contrast, brightness, and overall tone. This knowledge forms the foundation for many image processing techniques, including enhancement and segmentation. A histogram is a graphical representation of data distribution. On the right, you see an example histogram showing the distribution of letter grades in a class. The x-axis represents categories of grades, where each category is determined by an interval. For example, the letter A corresponds to scores from 90 to 100. The letter B corresponds to scores from 80 to 89. The letter C corresponds to scores from 70 to 79. The letter D corresponds to scores from 60 to 69, and the letter F corresponds to scores below 60. The y-axis, labeled as frequency, shows how many students fall into each grade interval. For instance, we can see that 50 students scored in the C range, while only a few students fell into the F range. This demonstrates how a histogram provides a clear summary of how data values are distributed across defined intervals. Frequency count is one of the fundamental ways to describe how data is distributed across a population. It refers to how many observations or data points fall into each category of interest. For example, in a student population, we might count how many students are male or female, how many belong to each age group, or how many received each letter grade. These counts give us a sense of the structure or pattern within the data, helping us understand how different characteristics are represented. Frequency counts are the foundation for building histograms, which take this raw count information and turn it into a graphical format that is much easier to analyze and interpret visually. When working with data, we often group values into categories, also called bins or classes. Each bin represents a range of values, such as 0 to 10 or 11 to 20. The count tells us how many data points fall into each bin. For example, if 5 data points in our dataset fall between 11 and 20, the count for that bin is 5. When we put together the counts from all the bins, we call this the histogram counts. These counts are the foundation for building histograms, which provide a visual way to understand how data is distributed. Assume we have 14 students. Their ages are shown at the top of the screen. On the left, we build a frequency table, also called histogram counts. This table shows how many students fall into each age category. For example, when we look at age 18, the frequency count is 0, meaning no students are 18 years old. Next, when we look at age 21, the frequency count is 5, meaning 5 students are 21 years old. Finally, when we plot all of these frequency counts as bars on the right, we obtain the histogram. The x-axis represents the age categories, and the y-axis represents the number of students in each category. This shows how the data points, in this case the student ages, are distributed across different categories. In the previous example, we created a bin for each age, resulting in 8 bins total. For example, bin 1 represents age 18, bin 2 represents age 19, and so on, up to age 25. Now, let's reduce the number of categories by combining 2 ages into one bin. In this new grouping, bin 1 represents ages 18 and 19, bin 2 represents ages 20 and 21, Bin 3 represents ages 22 and 23, and bin 4 represents ages 24 and 25. On the screen, the top chart shows the 8-bin histogram with 1-year intervals, while the bottom chart shows the 4-bin histogram with 2-year intervals. As you can observe, both histograms reveal the same overall trend in the data. However, the 8-bin histogram provides more detail by showing counts for each individual age, while the 4-bin histogram smooths out those details by grouping ages together. Each pixel in a grayscale image can be considered as a data point, with its intensity value ranging from 0, pure black, to 255, pure white. To describe the distribution of these pixel intensities, we can build an image histogram. For a grayscale image, this means we can have up to 256 bins, one for each possible intensity level. Just like we grouped students by age earlier to build a histogram, here we group pixels by their intensity values. The process follows 3 steps. Step 1. Choose the number of bins based on the intensity levels. Step 2. Count how many pixels fall into each bin. And Step 3. Plot these counts as a histogram. The resulting histogram provides a clear picture of how pixel intensities are distributed across the image. Assume IMG is a matrix representing a gray-level image, as shown on the top right. Now look at the highlighted statement. This statement performs a logical comparison between IMG and the value 5. The result is shown in the matrix named IDX at the bottom right. Here, a 1 means the pixel intensity equals 5, and a 0 means it does not. By counting the number of 1s in this logical matrix, we can determine how many pixels have intensity 5. This process allows us to count how many pixels fall into each intensity bin, which is a key step in building histograms. To obtain the number of pixels with a specific intensity, we can make use of the logical matrix. Instead of checking each element one by one, we can take advantage of MATLAB's sum function. By default, sum calculates the column sum of a matrix. When we apply it to a logical matrix, it adds up the ones in each column. For example, when comparing IMG with the value 5 and applying sum, we obtain a row vector. Each entry in that vector represents how many pixels with intensity 5 are present in the corresponding column. This approach is much faster than examining every pixel individually, and it becomes the foundation for building histogram counts. To obtain the total number of pixels with a specific intensity, we need the sum of the entire logical matrix. The first approach is to apply the sum function twice. The first sum computes the column sums, and the second sum adds them together to get the total. The second approach is to use the colon operator. The colon reshapes the matrix into a single column vector, and then applying sum gives us the total directly. To make this more flexible, we can replace the value 5 with a variable. That way, by changing the variable, we can count pixels of any chosen intensity. This total count corresponds to the frequency for that intensity bin in the histogram. Previously, we showed how to count pixels that match a single intensity value. However, in building histograms, many bins cover a range of values, such as all pixels with intensities between 18 and 19. To do this, we introduce 2 variables, a lower bound and an upper bound. We then compare the matrix against both bounds and take the logical AND of the results. The outcome is a count of all pixels whose intensities fall within that specified range. This generalization allows us to calculate frequencies for bins of any width, which is exactly how histograms represent groups of pixel intensities. In this unit, we introduced the core ideas of frequency counts and histograms. We learned that a frequency count tells us how many data points fall into a specific bin, and histogram counts are simply the collection of these counts across all bins. When plotted, these counts form a histogram, a powerful way to visualize the distribution of data. We also looked at how MATLAB supports this process. With logical indexing, we can find pixels of a specific intensity. With the sum function, we can efficiently count them. And by extending this method, we can handle bins that represent either a single value or a range of values. Together, these steps form the foundation for building image histograms, which describe the distribution of pixel intensities in an image. Now it's your turn. Complete the hands-on practice activity to apply what you've learned and reinforce these concepts.